Okay, hello everybody. My name is Charles Nyabeze, and I'm with the Center for Excellence in Mining Innovation. And I want to welcome everybody to this webinar where we're going to be talking about the future of blast design. And the company that's going to be doing the presentation is iRing, based out of Northern Ontario, North Bay. And they're going to be speaking to you about their Aegis software, which is a world-leading application for engineered design for blast ring design. And today we're going to be speaking to you about optimized mine to mill through blasting. And the iRing team, led by Mark Sherry, are going to be speaking to you in detail about the application so that we can bring everybody to speed on the future of blast design. So I'm going to hand it over to Mark Sherry so that he can continue the presentation. Go ahead, Mark.
Thanks, Charles. So as Charles mentioned, our sole focus is to underground drill and blasting, and we've been focused on this since 2002. And in the last probably about 5 years, we've been focused on fragmentation and how we can get the right fragmentation every time from every blast. And one of the first parts that we did with that was to create our brake module. And Troy is going to walk you through the scenarios that we can do in that in terms of case studies. So that's quite interesting. So I've got Troy Williams, our VP of Development, is going to do the presentation, and have Chris Preston as well online. Chris is a lot of the brains behind this information, and he'll be around at the end to ask any question too as well. So thank you, and I'll turn it over to Troy.
Thank you, Mark. So I'm going to talk a bit about the brake model, and I'm going to introduce it by telling you what it is and then how we worked with it to help a mine solve their problems. So our brake model is it's a two-dimensional single hole model that we've extended to 3 dimensions, and it looks at confined radial break and free face reflection. The confined radial breaks is how far the cracks will extend due to gas pressure on the blast hole walls. And the free face reflection is how the shock wave interacts with the free face. In order for the model to work well, we need to have a good understanding of the dynamic rock properties. We need to understand the explosive properties. And what this model will yield is an estimate of the optimal burden and spacing, your optimal pattern that you can use for the rock and the explosive combination. Now, for the rock properties, we need to understand the P wave velocity, the S wave velocity, the rock's density, and the static tensile strength of the rock. We're particularly interested in the tensile strength because we want to break the rock in tension. We have more control when we break the rock in tension as opposed to crushing the rock by overriding its compressive strength. The explosive, we're interested in the density as well as the detonation velocity, because the detonation velocity is key, as it will indicate how much energy is available to do the work of fragmenting the rock. And thirdly, we need to understand the shockwave attenuation in the material. That is, as the shockwave is traveling in the rock, how does it decay? How does it lose energy? And we typically get those measurements from the slope of the peak particle velocity curve. I'm going to start off by talking about a mine we were working with through a company called BBA. This is Éléonore mine in Quebec, and it is a narrow vein gold mine. Our goal was to design a blasting program to limit damage, reduce their fragmentation to 400 millimeters or less, and reduce their dilution. So the type of rock they were dealing with was gray wacky with a P wave velocity of about 6,000 meters per second, an S wave velocity of 3,400 meters per second. The density was 2.74, the tensile strength was 6.16, and the compressive strength was about 100 MPa. The explosive was a high strength emulsion, an ORCA product, Subtech Intense. The blast hole diameter was 100 millimeters, and the density was about 1.2. So the detonation velocity in that diameter is about 5,700 meters per second, which is very close to the P wave velocity of the rock. So the mine was having a lot of damage issues. So this is a picture of one of the stopes where they had extensive hanging wall damage. So you can see all of the damage that had occurred during this blast. This isn't what the stope should look like. You can see there's damage to the support infrastructure. As a consequence, they had a lot of overbreak, a lot of dilution issues, a lot of chunks. They had a lot of problems. But most importantly, once this damage started on one of these stopes, it would continue on up into stopes above and was very difficult to control at that point. I'm going to take you into our software to show you how we can run an analysis to see what's happening and understand what kind of solutions we could potentially provide. So this is our break model within our Aegis software. It's relatively simple to operate. We have a database where we would pre-enter the rock properties. I'm going to select the rock that we had for Eleanor. So we can see the properties. We've got the density, we've got the acoustic velocities. From the acoustic velocities, we calculate the dynamic modulus values. And from the static tensile strength, we can estimate the other strength values. With the explosive, one of the key properties is the detonation velocity curve. Eleanor had had test data for the detonation points, so we were able to nicely model the detonation velocity curve to get an accurate idea of how this explosive behaves in different blast hole conditions. If this sort of data is not available, we have pre-packaged curves for bulk emulsions, packaged emulsions, water gels, and ANFO in its various forms, so they can be used as well. Now, the attenuation curve, the slope of the attenuation curve, Eleanor had a lot of peak particle velocity data measured, and their slope averaged out to be about 0.94. But I'll show you how we can interpolate using a table we put together based on compressive strength of the material. So we put together a table that relates the compressive strength to a range of attenuation slopes. So Eleanor was at about 100 MPa, which puts it at the high end of the medium strength range and the low end of the medium high strength range. So what we would do is we would pick a value that's closer to the compressive strength that we're measured. So in this case, about 0.95. And it is actually a very close number to what they were actually measuring, in fact. So I'm going to use that value in the further calculations. All right, so 0.95. So the last part is to actually fill in the pattern dimensions that we want to analyze with the rock explosive system. So Eleanor was using 100 millimeter blast holes, fully coupled. They were using a 2.3 meter spacing and a 2 meter burden. That's all the data input we have to do for the software. The database, a lot of the issues we've been finding around using this in the field is actually having access to the data and understanding where it's located at the mine and who to talk to. But once the data is available, the analysis is relatively straightforward. So in this case, we're looking at the radial break component. That is how far we expect the cracks to extend due to gas pressure pushing on the blast hole walls. So we model that with 5 radial zones or 5 radial breaks. So we have the crush zone, the shatter zone, the minimum, the pattern, and the maximum. To give you an idea of what that looks like, I have a nice little diagram that illustrates it. So we have the blast hole here in the center, and this first zone is what we call the shatter zone. This is the volume of rock that's immediately adjacent to the explosive, and it's in intimate contact. This rock is subjected to catastrophic failure. It's subjected to borehole pressures in gigapascal range, so it's failed by an order of magnitude. So the rock in this zone we would expect to be very small particles. The second zone, we call this the shatter zone. And again, it's subjected to a tremendous amount of stress, not as much as the crush zone, but it's still very small particles. There's no strength for it to stand up. And then the zone we're interested in for production ring design is the zone 4. This is what we call the pattern break. It's a good zone where we can start to design the blasts around. And the 5th zone is where we would expect the limit of cracking to occur. We wouldn't expect many cracks beyond this zone. So what we do is we calculate the 5 radial zones, and we've estimated about a 2.1 meter radial break for our pattern. We also calculate a range as well. So what happens if the rock is actually weaker in tension? So if it's 30% weaker, we expect the cracks to travel farther. That is, if the tensile strength is less than what is 30% less than what we have listed in the database, we expect the cracks to go about 2.5 meters as opposed to 2.1. And if the rock in tension is actually stronger, we expect the cracks to not go as far as they would. And Eleanor had good data, so there's no reason for us to assume that this number is out of sorts. But if it were the case, we could actually perform this analysis a few times using the range. Now, the idea in this diagram down here is to take a look at the hole we're analyzing and compare it to a hole in the ring in front and an adjacent hole in the same ring to see how much overlap we have on the cracks. Now, we recommend the cracking be between, the overlap be between 2 and 12%. In this case, we're significantly over. We're in the 20% overlap, with cracking almost cracking to the next blast hole. Now, this is problem number one. The holes are too close, or there's just too much energy in this volume. Now, if we take a look at the stress distribution, this will complete the picture and help you understand some of the problems that were occurring in this particular blast. So with the stress distribution, we're looking at how the shock wave travels through the rock and loses energy as it's traveling towards the free face. This particular chart is a variant of what we would have as peak particle velocity. We've simply converted peak particle velocity to peak stress. And with that, we can actually estimate how far the shock wave can travel till it drops below a certain magnitude. For example, how far can it travel till it drops below the dynamic compressive strength or the dynamic tensile strength. So on the left-hand side, this vertical axis represents the blast hole wall, and this purple line represents the free face. So between the blast hole wall and free face is solid rock. Out here, we would consider it free face or air, where the rock is detached enough to be considered a free face. So the shock wave starts out at the blast hole wall at the magnitude of the detonation pressure. So in this case, we estimate the detonation pressure to be about 10 gigapascals. So the shock wave will travel outwards from the blast hole towards the free face. And as it's traveling, it's doing compressive damage and it's losing energy until it finally hits the free face, at which point we can calculate its stress at that point. So at the free face, it's approximately 300 MPa. So it hits the free face with 300 megapascals of force in compression. Now, since there is a very large density difference, an impedance mismatch between the rock and the ore, the majority of the energy is reflected back into the rock. So when it's reflected back, it changes mode from a compressive wave to a tensile wave. So from here, it travels in a tensile mode till it drops below the dynamic tensile strength on its way back towards the blast hole. Now, the disturbing part is when it changes mode, it starts out at 300 megapascals of tension, and our rock only has 15 megapascals of dynamic tensile strength, so it's doing a lot of damage. This is a good indication that they would get overbreak and a lot of damage into the hanging wall. A lot of spalling would occur because there's just too much energy in this volume. We have a different way to view this picture. We can actually view it using what we call our hyperbolic chart. So this is a plan view. The black dot here would represent our blast hole. This line would represent our free face. And these are in real units, which are in meters. So as the shock wave, as the explosive detonates, the shock wave, the rolling wave front travels out radially, strikes the free face and is reflected back in a tensile wave. So we can calculate how far that wave travels and establish a break hyperbola, which is the limit of the tensile strength. So essentially what we have is an area or volume in here that is affected by the tensile wave. And then overlaying our radial break, we have our area or volume that's affected by our compressive. Now you can see here our actual radial break exceeds our burden. So essentially our explosive is depressurized and is not working as effectively as it should. Ideally, the radial break would be approximately halfway to the free phase. So all of these point to reasons why this blast wasn't as successful as it should be. There's too much energy in the volume that they were trying to blast. Another way to look at this is our little table here. It's sort of a gamification style table. And the idea is to get green check marks in all of these rules. So there's only one green check mark. So overall, this wasn't a very good blast. There's just too much energy. So what can we do at this point with this information? Well, we need to reduce the amount of energy, and we can do that a few different ways. First, we can change the explosive product. We can move from an emulsion to something with less energy. We can change the blast hole diameter. We can decrease it to reduce the detonation velocity, thereby reducing the amount of energy, or we can increase the pattern, the burden and spacing. So let's see what happens if we change the explosive from the emulsion to an ANFO. So by changing it, you can see right away we've got many more green check marks, but our burden and spacing overlap are still a bit out. So let's take a look and see what that means. So what it means is that we have no overlap. Now in this case, this blast might be suitable. We might get close to the desired results. And looking at it through a bit of more of a microscope, what it means is that the volumes that are not touched by the radial break circle will probably break according to their in situ cracks, in situ joining and in situ cracks. So instead of being controlled by the blast, it will just be whatever the cracks are within. So this blast could be suitable. The other thing we can do is, instead of changing the explosive product, we can change the hole diameter. So if I put our original explosive back in and I reduce the hole diameter to 75, we can see, according to the model, this would produce a good blast. It's between 2 and 12%. And our break radius is very close to where it should be. It's not exceeding. And the reflection chart is actually hitting below the dynamic compressive strength, which is a good sign. This blast would probably work suitably as well, given the rock properties and explosive properties that we've listed in. Now the third thing we can do is increase our burden and spacing, and this is the route that the mine chose. They wanted to increase their pattern. So after a few iterations and a few rounds, we settled on this pattern, a 2.8 meter spacing and a 2.5 meter burden. So we can see we have almost all green check marks except for the ratio of the radial break to a free face distance. You can see we're at the upper end of our limit of 12%. We're very, very close, but we're within our range. So this blast should be good. And the stress distribution is actually just slightly below the dynamic compressive strength. You have to remember that this is a log-log plot, so small changes on the chart represent relatively large changes in reality. And this is our hyperbolic chart. So you can see it's in good shape. This could probably come back a little bit, but that's what this indicates. It means we've got some more wiggle room. Essentially what it means is we could probably expand the pattern a little bit more, but we were approaching the comfort limit of the mine and how far they wanted to expand the pattern. So what we did is we helped them design a blast based on those pattern qualifications. So when they finished designing their rings, they had planned for about 15,700 tons of ore, and they planned for about 9% dilution. So when they finished when they blasted the stope out and they finished extracting the muck, they pulled out about 15,668 tons. So the planned tonnage versus the actual tonnage was less than 0.2% difference. And you can see, most importantly to the mine, there was no damage. There was no damage to the hanging wall, no damage to the support infrastructure, no damage that would continue to ravel on up into the into adjacent stopes. And as a consequence, they had good control on the fragmentation. The crews indicated that the fragmentation was like gravel, some of the best blasting they've seen in a long time at the mine. There was very little dilution, far less than 9%. I think it was listed at about 7, and the particle sizes were well within acceptable ranges. To give you a little bit better idea of what this looks like, I have some 3D scans. So this white scan represents the prior stope with all the damage. That's this stope here. So you can see the bulge. So that gives you an idea how far out the damage extended, because the picture doesn't quite show it. And we had designed this adjacent stope, so the gold-shaped wireframe. It turned out really nice. The blast shape matched quite nicely. Overall, it was a really, really good, successful blast for the mine. Now, you might be wondering, this is all well and good, but I don't have all of this data at my site. And that's a common problem we've run into with mines throughout the world, is that they might have some of the data, but not all of it. They might not have other data. So I've got another case study that it relies on limited data. This is another mine in Northern Ontario. They were quite happy with their blasting. They didn't really want to change that, but they wanted to know if they could change from a very expensive bulk emulsion product to a less expensive a more expensive bulk emulsion product to a less expensive package. I said that the wrong way, my apologies. It was the packaged product they were using. They wanted to switch to the bulk emulsion, which was approximately half the cost. They had no peak particle velocity data. They didn't have any VOD data. What we did know, the pattern. It was a 5 foot by 5 foot pattern with a 3-inch hole diameter, and they were using decoupled charges on the hanging wall side to try and preserve the hanging wall. They were using DynoSL, and we had to estimate everything else. We estimated the rock properties, we estimated density and structure. We estimated based on some of the mines in the area that we know about, but the one saving grace that allowed us to perform an analysis is they had CMS data. So what we did was we ran the data, our estimates through our model, and we predicted a radial break of about 4.8 feet. But when we overlaid that against the CMS, we could see we were over breaking compared to what the CMS was actually measuring. So this purple shape is our estimate, and the white shape is the CMS. So you can see the effect of the decoupled charges on the hanging wall. So we have to ignore that for now, because at the time we didn't have a way to account for the decoupled charges. That's changed since then. So if we take a look at this, we can actually measure and determine that we overestimated the break by about 2 feet. So you can see on here. So what we did was we were actually able to go into AGIS, and we're actually able to calibrate your rock type. So based on our estimates, we were able to change the tensile strength to suit the radial break that we were measuring from the CMS. So we calibrated that number, and we ended up calibrating the model so that we could actually predict a radial break based on their CMSs. And once we ran that through, we were able to get a much better fit on our surface generation. So you can see we have good agreement here between the CMS and our generated radial break, which meant that we could proceed with the rest of the analysis. And it turns out that they would be able to switch from the packaged product to the bulk emulsion, thereby saving half their explosive costs right there. And in fact, according to our numbers, it looked like the bulk emulsion was had a little bit more energy, so they would be able to actually expand the pattern somewhat, and thereby potentially save drilling costs. So another interesting innovation that we're coming out with as a direct result of the experiences we're having in the field is we're coming to market with a new type of stress probe. We call it the rock scan, and it's designed for underground use and surface as well. And it's designed to measure background static stresses. It's particularly well suited for the dynamic blasting events. You can also measure strain changes to vital structures such as pillars and potentially monitor for rock bursts. But for us, the important part is that we can use the data to estimate the properties we need to feed our models. Now here's an example of a typical chart you might see. It starts out at a particular stress level here, and it bounces around measuring the incoming stresses of each of the holes, depending on the timing. And finally, after a certain point, it settles down to a new stress level. In fact, in this particular case, the stress level increased in the area where the probe was set up. So instead of reducing the stress, we've increased the stress in that area. And that's it for me. I'm going to turn it over to Mark. Mark, are you there? All right. So our future plans, we're going to be augmenting our break model with a fragmentation prediction model. We're about probably 6 months out on having that in place. That's why I was a little vague on the particle sizes in each of those radial zones. They'll be extended so they'll have their own fragmentation distribution. We'll be able to apply that model to each of the holes in the blast to predict fragmentation at within any volume as part of the blast. The rock scan, the geomechanical instrument will be ready. We'll probably finish the production at the end of the month. Not the end of the month, but the end of the year. We hope to have it to market by that time. And some of the other aspects of Aegis of our software will be adding drifting and lateral development, which will all tie into fragmentation and whatnot.
I can take it from here, Troy. Sorry, my mute was turned
Okay.
off. So thanks, Troy. There's just a couple things. If you go to our website, we actually post a lot of articles, and you can just, when you download them, you can sign up, and then we'll send you the articles monthly basis. And these are our technical articles about anything to do with blasting and drilling. So have a look at those. And then finally, we have an extensive knowledge base on our website. Literally hundreds or thousands of articles about everything you ever want to know about underground drill and blast design or drill and blast design in general. Mostly put together by Chris Preston, who is the brains behind this knowledge base. So it's like having Chris Preston in your office. So if you need to look for anything, it's free, and it's on our website. So help yourself to that. And I guess I'm going to turn it back over to Charles to see if any questions are out there.
All right, thank you very much, Troy and Mark. Our first question is from Mohammed, and the question to iRing is, could the fragmentation size be controlled by the timing sequence and firing pattern?
Chris, did you want to get that one?
I think you might have to unmute him, Charles.
Okay, I'm just gonna go for him. Chris, give me 1 second, please.
That's the issue I was having.
But yes, timing is a key factor in fragmentation. Chris will have a more extensive answer for that.
And that's going to be built into our fragmentation engine as well.
Okay, I think Chris is unmuted now.
Yeah, I was just going to add the fact that we found a very interesting correlation between increasing the time between rings so that they're not all firing at the same time increment. And we found that you can pack the muck in such a way that more void space is created. In order to do that, what you have to do is if a ring fires at 100 milliseconds or later, what you have to do is you have to account for the time it takes for the muck to get now double the distance. And so you add a few milliseconds to that. And really that is supposed to make sure that the free face for the next ring to fire is pretty much unburdened. And what happens is that you're constantly blasting to the pattern burden when you take into account the timing going from ring to ring. You really don't want to burden up the next ring to blast. So timing is very, very crucial to get the fragmentation you need. And we have found that when you get to that stage of getting fragmentation that is predictable from blast to blast to blast, you can now look at perhaps mollifying the crusher costs, and perhaps even at some stage take the crusher out of the picture altogether. And what Troy showed you was a mine that based its economics on not having a crusher underground. So the model certainly works.
I think we got a few more questions. So
I'd like to just add to that about the Eleanor project. We did an excellent design, but it was the gentleman by the name of Daniel Roy at BBA who was on site and ensured that the holes were drilled where they needed to be drilled, and they were loaded and timed correctly. We had to have that part in, otherwise the best laid plans wouldn't work. All right.
Thank you for that. We do have many questions, and seeing that we are near the end of our timing, we'll just move through them quickly. Next question is from Adrian, and the question is, does the break model actually generate an estimate of the fragmentation distribution?
I'll answer that. We are staying away from the Kuzram model for predicting fragmentation. The reasons being that we seem to find it case specific, and it's mostly applicable to open pit mining. And we are working on a fragmentation model right now that is based on tensile and shear failure, which takes the Kuzram model right out of the picture. And we're hoping to have that done by the end of the year. So we get the fragmentation from the break model that has already been peer reviewed and has performed very well.
Thank you for that. Another question is there a possibility to have a trial on the Aegis blast design software?
Yes, that's definitely possible.
yeah, just contact us and we'll set it up.
Okay, another question from Anna is, how does this technology help to optimize the ore sorting and other downstream technologies? What can be done to reduce the variability of rock size for mill inputs?
Well, what we are trying to do, the whole objective is you've got a very powerful brake engine to begin with when you're loading rings with explosives. And one of the difficulties in underground mining is the fact that all the holes are pretty much oblique. So it differs vastly from surface blasting where holes are parallel. So you have to take into account things like brake overlaps between one hole and another hole and the ring behind. So we're getting very close to be able to get rid of the crushing that would be done by a primary crusher underground. So we expect perhaps in another year or so, we'll have the fragmentation model built, which is built on the tensile shear failure that you see in a blast. And the fragmentation should be able to be predicted from one blast to the next.
We're trying to jump as far down the milling cycle as we can. So, you know, our goal, we think we can eliminate somewhere between 25 and 50% of the energy used in that process if we can get the fragmentation consistent every time.
Yeah, now the key to that is we're looking at targeting, we're designing a blast so that it meets a specific fragmentation distribution. So if you have size ranges that you need for ore sorting, you would design a blast that would target that. Ultimately, we're looking at designing blasts that target fragmentation that bypasses primary crushing, secondary crushing, and takes it as far down that circuit as possible. Charles, another question, or do we have time?
Yes, just one more question. Does the model take into account for hole deviation?
Yes, that's an integral part. We can bring holes that are surveyed into the product and use those as a basis. They'll be definitely a basis to the 3D fragmentation model. The reality is what we're trying to model here.
Okay.
Chris, do you have anything else to add?
No, I just would complement what you said, and that is bringing already surveyed holes into the program. You can go ahead and blast it and see if that blast will turn out the way it should, or whether you should go back in and re-drill. So we're able to import surveyed holes and blast them in the model.
Maybe we'll just take one more question, guys, in the interest of time. The other question is, please comment on both drilling and loading practices, especially the importance of quality drilling.
Drilling is a paramount importance. What you're trying to do is you're trying to place energy in an ore mass strategically, so that energy is conserved from the collar to the toe. And I think what you need to do is make sure that the drilling specs are accurate, so that you might want to go and survey holes to make sure that they're at least close to plan. And the other thing too is that there are companies that are coming out with their own drilling packages that fit on a drill and are able to actually drill and measure at the same time in order to make sure that the holes are where they should be. And that company is called Minover, and they provide an attachment that sits on the drill that's interconnected with the drilling controls that will puts enough smarts in the system to make sure that the holes are drilled within a certain specification.
And drill manufacturers of all types are coming up with that same type of system, I think, on the newer drills.
All right. Okay, folks, seeing that we've reached the end of our presentation and went over a little bit, I want to thank everybody for coming online. And what we will be doing is we will be forwarding you a link to the recording of this webinar, and we'll also make available the slides. And within those slides will be contact information on how you can reach the folks over at iRing, or you can just speak to us at SEMI and we'll be able to forward you to the right person at iRing. Again, thank you very much for your time, and we look forward to engaging you post this webinar. Thank you, everybody. Have a good day.
Thank you.